This is example 2 for the column buckling section. We're given a steel channel, A36 steel. It has a load of 10,000 pounds on this particular column. We have a safety factor of 2 against buckling. The column itself is pinned and it's 15 feet long. So our question, or what we're asked to find, is what is the cheapest standard section that meets these requirements? So we're looking for an actual section reference. In the same way that I did the last problem, I started with my mathematical model. I have P critical as an Euler buckling equation. We have listed out P critical is the critical buckling load in pounds. E is the modulus of elasticity of the column material. That's the steel in PSI. I is the moment of inertia of the column section about the buckling axis, which we will need to determine. L will be the length of the column in inches. I looked up in table F2 the material properties for A36 steel. We have modulus of 29 million psi and a yield strength of 36,000 psi. The geometric properties for this channel section are unknown because the channel section itself is unknown. But I'm going to limit the sections that I consider to those that are in table D4. The reality is there are many more that exist. This is just a very limited table. The factors that are considered in the system modeling are that they say it's a column with a pinned end conditions. And when we say that for a column, generally, again, we mean 1 degree of freedom at the bottom and 2 degrees of freedom at the top, so that the top of the column can move not only rotationally, but also vertically. I'll draw that here. We know we're loaded axially. And I'm going to assume only. What this will do is help us with our AX and BX when we get to our free body diagram. And finally, I want to go ahead and look at how this column is oriented in our model. If a channel section generally has a section like this, and if this is the way that it's oriented, with an X direction and a Y direction, then I'm going to go ahead and say that this is the plan view of this column. This will be the side view. And therefore, I will have this web as a hidden line in my channel over here against the left-hand side. So I hope you can see that. We will end up having buckling out of the plane in the weak direction, which will end up being in this direction. That's why I drew it the way I did. Yeah, it's kind of off there, but you get the idea. Well, let's see if we can fix it. Look at that. The amazement of technology we have. Okay, let's move on. to our free body diagram. I'm going to go ahead and start drawing it as our channel, again in plan view. I went too far. I will go ahead and still put my nodes in, because all loads happen at the nodes. I did not say that on purpose that way. Loads happen at the nodes. Okay, we know we have reactions of AY and AX, BX, and there is no BY. Remember, there was only 2 degrees of freedom. There were 2 degrees of freedom at the top. However, our loading does come through P in the X direction or Y direction. So we have our standard global coordinate system here. All right, because it was loaded axially, we know that BX and BY will, AX and BX will be 0. And so we're left with a pretty simple column with a length of, what did we say, 15 feet? Which I believe is 180 inches. Okay. Now let's move on to our calculations. I went ahead and assumed that our critical buckling load for the column is P critical, which is our standard Euler equation, referenced earlier as equation 1. But for our case, we're not really asked to calculate P critical. In our case, we are asked to design for a factor of safety equal to 2 for a load with a load of P equals 10,000. So really what we need is a relationship between our load and P critical. We get this through our safety factor equation. Our safety factor equation is factor of safety equals 2, and that's equal to P critical over P. So the failure load over the actual load, we want P times 2 to be equal to the critical load. This is going to be my equation 2. Solving for P critical, and I should say solving equation 2 for P critical, P critical equals 2P. I'm going to go ahead and plug in my value of P. And I get a P critical of 20,000. I can plug this into my equation 1. So my P critical is 20,000 pounds. That's pi squared EI over L squared. We'll go ahead and call this equation 4. Now I can plug in, I'm sorry, I misspoke. We can solve equation 4 for I, which is what we need. In this case, I is going to be equal to this 20,000 pounds times our L squared, 180 inches. We're going to divide by pi squared, and E, we said was 29 million. And that's pounds per square inch. This is my equation 5. Doing my little unit analysis on the side here, I have pounds and inches squared. I have pounds and inches squared. So the pounds cancel, and I end up with inches to the 4th, which is what I want. All right, so when I calculate this all out, this represents my minimum I value needed to achieve our desired results. And I get 2.26 inches to the 4th. And I'm going to call that our I required. But again, is this what we're looking for? Were we asked at the beginning of the problem for an I? No, we were asked to pick a section. So the next step is to pick a section. I'm going to move on to the next page to give myself some room. And I'm going to annotate my thought process here. Now, in table D4, the IY values, I sub Y values, for a few channels that meet this I minimum requirement are shown below. Okay, so I'm going to make a table of the different sections and their respective IYs in inches to the 4th. Okay, and if my I minimum is the 2.26 inches to the 4th, then I have to pick values where I is larger. So I look through the table and I can see a C9 by 20, and that has an IY of 2.42 inches to the 4th, and a C10 by 15.3 that has 2.28 for an IY value, and I see also a C10 by 20, and that has 2.81. Yeah, I think those are right. Now, note here that all of these are greater than the minimum required. They all serve the condition and will meet our expected safety factor value. However, we were asked to give the smallest one. And so in this case, the C10 by 15.3 is our smallest, and therefore the cheapest. So the final answer in the final analysis, a C10 by 15.3 has an IY value of 2.28 inches to the 4th, and this meets all the requirements for the design, and it is the cheapest section. So there you go. That's the end of that problem.